And my main goal is not to teach you anything. I think it's very difficult to teach anything properly in 1.5 hours. What I want to do today is to get you excited about the possibilities that machine learning offers you to, to make your research better. I don't like the term artificial intelligence. I usually just say that I'm doing machine learning. This is a very new field, and it's advancing and changing very rapidly. My feeling right now is that I'm growing more ignorant every day on this field. So I like to...
The first section I found really meaningful was when he defined what a machine learning model was.
What is a model? And how a machine learning model is different from, let's say, a physical model. So imagine that you have a one-dimensional harmonic oscillator, and there are some equations of motion for that, and we can measure, if we're doing an experiment, the position of the mass as a function of time. We can also solve Hamilton's equations to predict. So this defines kind of everything that can be observed about the spring. So how would we describe the one-dimensional harmonic oscillator with a machine learning model that doesn't know physics, doesn't know Hamilton's equations of motion? One prior assumption, and this is actually called a prior, is that we want our model to be smooth. So we don't want spikes in the predictions and so on. So all of those green lines are smooth models attempting to describe the harmonic oscillator. As you can see, the true solution is the purple one. All of these models are rubbish, but they're smooth. So instead of physics, we don't know the physics, because we're just going to do machine learning. We need to use data. So we add data. We condition all those models to be compatible with that data. And that's the only thing, in addition to being smooth, the only thing that all of those models have in common is that they predict that data point. So let's add more data. Right now we're starting to collapse all of these smooth models onto something that resembles the actual solution. And the predictions in between data points and our model is really, really good there. Now we don't have any data here. Our model is extrapolating. It's really bad here. So the natural conclusion of this, or the naive conclusion, would be that if you want your model to behave better in a region of what we call the configuration space, then you need to add more data within that region. Otherwise, you have no guarantee that your model is going to do anything sensible.
The second section that really interested me was what got him interested in machine learning in the first place.
My journey to become a user and also a developer of machine learning for atomistic modeling, understanding the structure of amorphous carbon-based materials. So let's start easy and try to answer the question, which was the question that I was trying to answer in 2016. What does chemically pure amorphous carbon look like? So amorphous carbon is usually grown through some physical vapor deposition process where you deposit highly energetic atoms onto a growing film. And you have the incoming atom there in red. It is actually coming very, very hot. It's like 1 million Kelvin. You can see that the atom impacts the film. There is a thermal spike. There's lots of bond breaking, lots of bond formation taking place. This is chemically very complex. You need a very sophisticated model of the potential energy surface to be able to do this accurately. You cannot do this with DFT because this is just too big. It would be too expensive to do a DFT calculation of this. And on top of that, it's not just one impact. You need to repeat this many thousands of times. There were something of the order of 60 bond breaking and formation events per impact. Here you can see how the film grows. For 1 EV incident energy, right? You do this literally 10,000 times, and you can start to study the structure of the material. We changed the incident energy, repeated the deposition simulations, and we got for the first time very good agreement between structural models of amorphous carbon and what was available from experiment. So this was it was a great demonstration of power that really convinced me to essentially direct my entire career in this direction. I wanted to show them how professional researchers have successfully used machine learning in their research. So I just wanted to get them excited about the possibility of embracing machine learning for their own research. So it was more of some sort of emotional response that I was expecting from them more than actually teaching them any physics or chemistry.